Okay, in this fourth part of the lecture, I want to introduce a geometrical representation of least squares, which I think is useful in understanding the least squares estimated in a linear model in a deeper way, particularly in getting to grips with the matrix algebra and how it all comes together. It's also useful in emphasising the importance of the relationship between the design matrix X and E, and this idea that they have to be independent, or what we're going to call orthogonal, and it really demonstrates why that has to be the case. And also we'll be able to introduce some concepts that we'll use as we go forward in this course. So, least squares has a geometric interpretation which can provide a useful alternative perspective. We're going to view the least squares estimator as an orthogonal projection into the column space of X, and we'll define what these terms mean in just a minute. But importantly, what this is going to do is it's going to allow us to algebraically derive the least squares estimator, beta hat, without using calculus or without using optimization. We're going to do it just by making some assumptions about the geometrical relationship between the design matrix X and the error vector E. So we're going to view least squares as an orthogonal projection into the column space of X, and we'll start by defining what those components of this perspective mean. First, column space. The column space of a matrix is the vector space spanned by its column vectors. So in our case, we have a matrix with k plus 1 columns, so the column space of X is simply the k plus 1 dimensional linear subspace spanned by its columns. So we're going to look in a minute at this diagram here, in which X has only two columns, x1 and x2, and in this diagram the column space of X is represented by the yellow hyperplane. This is the space that is spanned by the vectors x1 and x2, which are the columns of X. Okay, we're going to talk about a projection into column space, and a projection mathematically is simply a function that maps a set onto a subset. Our projection is orthogonal, and most of you will know what orthogonal means, but when we're talking about vectors, two non-zero vectors A and B are said to be orthogonal. That is, they meet at right angles. If and only if this condition holds, the transpose of A times B is equal to the transpose of B times A, which is equal to 0. So for two orthogonal vectors, the inner product of those vectors will equal 0. And then the next definition concerns the length or norm of a vector. The length or the norm of a vector, E, the vector bold E, is given by Pythagoras' theorem. So length or norm of a vector is the square root of the inner product of the transpose of the vector times the vector. So that's the definitions we need. That's the only definitions we need to now go on and look at least squares as a projection of y into the column space of X. So an arbitrary vector, let's call it V, is said to be in the column space of X if it can be expressed as an exact combination of the columns of X. So let's take our multiple linear regression model. Y equals x beta plus E. Y, our dependent vector, our vector of dependent variables y, is clearly not in the column space of X. If it was in the column space of X, there would be no error, and beta would give us an exact solution. The vector beta, we'd be able to find a vector beta that gives us an exact solution of X, and there'd be no error. So we could solve directly for beta, no error, and we would have a perfect regression model fit. The least squares estimator actually finds a vector beta that is an exact combination of the columns of X, and in that sense we can view the least squares estimator beta hat as being an orthogonal projection of y into the column space of X that's achieved by forming fitted values that sit within the column space of X. Those fitted values are in there because they can be expressed as an exact combination of the columns of X. And this is shown diagrammatically here. So as I said, in this diagram, X only has two columns, x1 and x2. As we've said, our output vector y doesn't lie in the column space of x. It's sitting up here above the hyperplane. What least squares does is it projects, it creates an orthogonal projection of y into the subspace, into the column space of x. And it does that through y hat. Y hat is in the column space of x. You can see it sitting down here. It does lie in that column space because it can be expressed as an exact combination of x. And so what least squares does is it projects y into the column space. That's the way we can view it. Now, in achieving that projection, we produce an error vector. The error vector is the difference between the column vector y and the fitted values. And that column vector is orthogonal. That's what's meant by an orthogonal projection. So it's projected orthogonally into the column space of x. That is at right angles. And the condition we need to ensure that it's orthogonal is that x transpose e equals 0. Bear in mind that this is a vector of zeros. So in other words, every column of x times transpose times the vector e has to equal 0. These, each column and the error vector have to be at right angles. This inner product has to equal 0. So that's what least squares is doing. It's projecting y into the column space. It's doing it through these fitted values, and that produces an error. But due to Pythagoras' theorem, as long as these error terms are orthogonal to the column space, it must be the case that e is of minimum length. That's what Pythagoras' theorem tells us. And therefore, the y hat that we obtain through least squares estimation is the closest point to y in the column space of x. Or in other words, the error vector is of minimum length. So the question is, how do we know what projection we need to, how can we compute the projection that gets us into the column space of x? How does that work? Well, in order to do that, we're simply going to use this condition here, that it has to be an orthogonal projection. So the fact that x transpose e equals 0, and therefore for every column of x, x transpose e equals 0, allows us to compute the orthogonal projection. And in doing so, we're going to define this hat matrix of least squares. So the first point I want you to note, and this is a nice point to note, is without any calculus, simply from this orthogonality condition, we're going to be able to arrive at the normal equations. So if x transpose e equals 0, as we must have for an orthogonal projection, e being orthogonal to this column space of x, then we expand that out. X transpose y minus x beta has to equal 0, or x transpose y minus x transpose x beta equals 0, and that is simply the normal equations that we derived in another way using matrix calculations and optimization, so using calculus. So from this expression alone, just by making this assumption, we can derive beta hat as x transpose x minus 1, x transpose y. We've just used that expression there. Once we know beta, that allows us to form our orthogonal projection, because our orthogonal projection then must be y hat, the y that's projected into the column space of x, is equal to x times hat beta. So it's equal to x transpose x minus 1, x transpose y. And this matrix here, we call it H. This matrix here, we call the hat matrix, because that's the term that puts the hat onto y. So we multiply column vector y by this expression here, and it puts a hat on y. And we call that the hat matrix. We also call it the projection matrix for the obvious reason that it is a matrix formed from x that projects the vector y into the column space of x, and it has some important properties. It's symmetric, it's idempotent, and if we multiply x by h, then we get back to x. So this is quite an interesting way of looking at least squares. As I said, no calculus, and yet we've derived the least squares estimate, and we've been able to look at what the fitted values are. So I want to just finish this section by making some observations on the hat matrix and its associated orthogonal projection. If a vector v is in the column space of x, then a property of the hat matrix is that p multiplication of e by h pre-multiplication of v, by h, will get us back to v. So for example, we know that x beta, we know the fitted values are in the column space of x because the fitted values can be expressed as an exact combination of x through beta hat. If we multiply hv, or in this case h times the fitted value, we get this expression here, which gets us back to x beta hat, which equals v. So h times v, if v is in the column space, will always return the vector that is in the column space. If v is perpendicular to the column space, on the other hand, then hv will equal 0. So for example, defining v this time as our error vector, which we can write in this form here, again in this form here, if you just go through the calculations, you'll find that pre-multiplying the error vector by h produces 0 because they're perpendicular. The principle of these squares then, viewed geometrically, is that we're using h to project y into x with the product y hat being in the column space of x. That is, y hat is a combination of the columns of x. And in fact, y, as we've shown in diagrammatically, is the closest point to y in the column space, and that's due to the projection achieving minimum distance simply through Pythagoras theorem. To see the Pythagorean theorem at work in the sum of squares, note that by choosing hy as the orthogonal projection of y into the space spanned by the column of x, we produce this error vector. Writing y as the sum of the fitted values plus the error vector, we note from the argument above that these two vectors must be orthogonal. That is, y hat transpose e must be y hat transpose e, that inner product, must equal 0. And of course they must be orthogonal simply because y is in the column space of x and e is not. It's orthogonal to it. So the length of e then is minimized by choosing this fitted value x beta hat as the orthogonal projection of y into the space spanned by the column of x. The residual sum of squares is simply the square of the length of the residual vector. And these two things, therefore, are equivalent. That's why there's equivalence between the geometric interpretation of these squares and the calculus interpretation. Calculus minimizes this thing. Geometrically, this is also minimized because it's orthogonal, and by Pythagoras theorem, it must be minimum distance. So the fact that beta OLS produces the minimum length vector e when it's orthogonal to the hyperplane that constitutes the solution locus also corresponds to it being the solution that minimizes the residual sum of the squares.